we are looking forward to your talk.
Great, thanks a lot. And just to clarify, should I be recording, or you said that?
I already pressed the recording button and it's recorded to the cloud.
Excellent, thanks. Okay, so I'd like to start off, of course, by thanking the organizers. I think it's been great to give students an opportunity to present some of their work, especially given that kind of in-person conferences aren't necessarily feasible right now. So I think this has been really great. So today I'm going to be talking about some work with my advisor, Mark van Ramstonk, regarding a calculation of a quantity called the boundary free energy in n=4 super Yang-Mills theory. So I'll start off with kind of a more familiar story. So in general, we can think about associating a UV complete quantum field theory with some RG flow between CFT in the UV and then some CFT in the IR, where we perhaps deform by some relevant operator in order to move along the flow. One useful tool for trying to analyze these possible RG flows comes in the form of a C theorem, which essentially posits the existence of some function on the space of quantum field theory couplings called a C function. And this function obeys certain properties, namely it is monotonically decreasing along RG flows. And then at the endpoints of an RG flow, it coincides with some scale invariant function like the central charge of two-dimensional CFT. So C theorems are well established in various low dimensions, namely 2D, 3D, 4D CFTs. But in general, one might want to ask if one could try to generalize this notion to higher dimensional quantum field theories. And so some candidate C function that we can think about trying to analyze is a certain universal term which appears in the vacuum entanglement entropy of a ball-shaped region in quantum field theory. So this is sometimes called generalized F in analogy to the three-dimensional case. And this is some natural generalization of the results from lower dimension. So in general, if we consider the entanglement entropy of this kind of a ball-shaped region, we'll get some scheme-dependent terms, which are essentially powers of the some UV regulator, but then there will also be some universal terms appearing in this expression. And the conjecture of the generalized F theorem is that these universal terms constitute good C functions. One nice fact, which I'll mention now because it is kind of useful later, is that this universal term can alternatively be calculated by considering the partition function for the theory on a sphere and calculating the associated free energy. And then the universal terms appearing in that expression coincide with the universal term that we are talking about in the entanglement entropy, thanks to a famous relation by Cassini-Huerta-Myers. Now, so this is a nice story, and then we might be interested in trying to extend it to a case where we add some boundary to our theory. So in general, we can think about taking some d-dimensional CFT and then adding some boundary and imposing some kind of a conformally invariant boundary condition at this newly added boundary, and then possibly also coupling in some extra degrees of freedom at the boundary. And this kind of a construction leads us to something called a boundary conformal field theory, or BCFT, which has been sort of an interesting object of study for decades, but is especially in vogue in the last few years. So one might try to apply some similar considerations in this context. So we might be interested in studying RG flows between different BCFTs. In particular, we might want to consider flows between two BCFTs which correspond to the same bulk CFT, but maybe correspond to applying different boundary conditions within that CFT. And so in order to kind of move between these two different boundary conditions, one can think about applying some deformation by a boundary operator, and then there's some resultant boundary RG flow that moves us between the two BCFTs. So analogizing with our previous discussion, we might consider the entanglement entropy for some half-ball region, which is centered at the boundary of the BCFT. So this entanglement entropy is again going to have some UV divergences. This time the UV divergences are both d-dimensional and d-1 dimensional in origin, because we have this d-1 dimensional boundary. But we're going to want to, again, try to extract some universal contribution. And the way to do this, in analogy with the famous G function of 2D BCFT, is to define a boundary entropy by an appropriate subtraction. Namely, we take this half-ball entanglement entropy from the BCFT and we subtract some contribution which corresponds to the entanglement entropy of a ball-shaped region in the original CFT. And so the result has this kind of the general form that we might expect for the entanglement entropy of a ball-shaped region in D-1 dimensional theories. So it will again have some scheme-dependent terms, but then there will be some universal terms appearing. And the conjecture of the boundary F theorem is that these universal terms are monotone under boundary RG flows. And again, I'll just mention that there's some way that you can compute this universal term appearing in the boundary entropy by considering the partition function for the theory on a hemisphere. So just to summarize kind of what's known about this conjecture. So the cases of 2 and 3 dimensions are established previously, but the 4-dimensional boundary F theorem remains a conjecture with kind of supporting evidence from certain boundary conditions of n equals 4 super Yang-Mills theory, or from free theories, or from the critical ON model coming from various authors. But it's a natural question to ask whether this boundary F theorem actually holds in general dimensions. And so kind of a natural place to start investigating this claim is to try to actually calculate boundary F in some of the most tractable theories that we can think of. And this leads us kind of naturally to consider everyone's favorite theory, n equals 4 super Yang-Mills, with some maximally supersymmetric boundary conditions. So there are a few nice features about this, this class of theories. One is that there was a very detailed classification of the OSP 224 preserving boundary conditions of n equals 4 super Yang-Mills undertaken by Gallardo and Witten in the early 2000s. Additionally, the holographic duals for the vacuum states of these theories are known explicitly in type 2b supergravity. And also in certain cases, the partition function is readily amenable to direct calculation via supersymmetric localization. And we can actually import some previous nice results for the calculation of the partition function of n equals 2 supersymmetric gauge theories in 3D and 4D. So our mission in this talk is essentially going to be to compute this quantity, boundary F, in n equals 4 super Yang-Mills theory with half supersymmetric boundary conditions. And as a kind of preemptive spoiler, what we're able to find is for the most general such boundary conditions, we can compute boundary F in complete generality from a holographic calculation in the classical supergravity duals. And specifically for a generalized Dirichlet or a generalized Neumann boundary condition, we're able to compute an exact expression for boundary F using localization. And what we find is that boundary F behaves basically as we would expect for a measure of the local boundary degrees of freedom. We see that in particular for small to Hooft coupling, the Dirichlet type boundary conditions lead to predominantly negative values for boundary F. This kind of has a natural interpretation as this kind of boundary condition corresponds somehow to giving some position dependent mass terms, which are eating up degrees of freedom close to the boundary. Whereas for Neumann type boundary conditions, we find that boundary F is predominantly positive, which again matches our intuition that these boundary conditions somehow correspond to coupling in extra degrees of freedom at the boundary. And we also find that boundary F is unbounded from above, which agrees with the idea that we should be able to couple in arbitrarily many boundary degrees of freedom. So I'll get into some of the details of this calculation now, but I guess I'll start off with reviewing the classification of these boundary conditions. So in general, if we start off in the n equals 4 super Yang-Mills theory, we have some fields appearing in the 4D n equals 4 multiplet, including the gauge field, some fermion field, and then 6 real scalars, which transform in the fundamental of the SO6 R symmetry. Now, if we think about adding some maximally supersymmetry preserving boundary at the 0 position of the x3 coordinate, we choose to put the boundary in the x3 coordinate by convention, then the 4D n equals 4 supersymmetries are going to break to some subgroup, which is the 3D n equals 4. The R symmetry also is going to break from SO6 to 2 copies of SO3. And then our original multiplet is going to decompose with respect to the reduced supersymmetry to a 3D n equals 4 vector multiplet and a 3D n equals 4 hypermultiplet. And somehow the idea is that when we're trying to construct our general boundary conditions, we will be imposing different independent boundary conditions on these 2 3D multiplets, and then possibly coupling in some extra degrees of freedom at the boundary. A useful picture to try to keep in mind throughout this discussion is the string theory picture, where we have some half BPS configuration of D3-branes ending on D5-branes and NS5-branes. So in general, the low energy description of this kind of a configuration is going to correspond to the theories that we're talking about. And for our conventions, we're going to think about having the D3-branes be semi-infinite in the X3 direction, and then ending on D5s and NS5s, which are in general separated in the X3 direction, although this separation will become negligible when we consider the IR limit. And also the D5s and NS5s are oriented in a way which makes the configuration half BPS, but involves the D5s and NS5s occupying different sets of transverse coordinates. So what data do we need to completely specify our boundary condition? Essentially, we need a list of integers associated with the D5-branes and a list of integers associated with the NS5-branes. So these are called linking numbers. We denote the D5 linking numbers with L and the NS5 linking numbers with K throughout this talk. And basically, we associate some integer to every 5-brane appearing in our configuration. And in the string theory picture, the linking number essentially is equal to the net number of D3-branes, which end on the 5-brane from the right, plus the number of 5-branes of the opposite type, which appear at smaller values of the X3 coordinate. So I guess as an example, in the diagram shown here, we can think about the NS5-brane, which is at the left of the diagram. So the net number of D3-branes ending on this NS5-brane is 4. But to get the linking number, we would also have to add the number of D5-branes, which appear to the left of the NS5-brane in this diagram. So just as an example of the kind of a general boundary condition that we could have, here we just have some collection of D3-branes ending on NS5-branes and D5-branes in this schematic diagram. And there's some canonical ordering that we can choose for the 5-branes, where we move the NS5-branes to the left and make all of the linking numbers non-decreasing. And this ordering can be done without any concern for altering the low energy physics of the construction. A couple of sort of natural boundary conditions to consider. One is the classic Neumann boundary condition, where we impose a Neumann condition on the 3D vector multiplet and a Dirichlet on the 3D hypermultiplet. And then in the brane picture, this just corresponds to having all of the D3-branes end on a single NS5-brane. A slightly more interesting example is the generalized Dirichlet boundary condition. So here we apply just some normal Dirichlet boundary condition on the 3D vector. But we have some supersymmetric nom-pole for the 3D hypermultiplet. So the equation shown here in red is sometimes called the nom equation, and this constitutes the boundary condition for the scalars appearing in our 3D n=4 hypermultiplet. And the solution comes in the form of a nom-pole. So basically, these scalar fields have some simple pole at the kind of x3 = 0 position. And the coefficient matrices here, these Ti appearing in this expression, they're just a triple of matrices which obey some SU2 algebra. And the way we can determine what the Ti's are in terms of the brane picture is essentially that the dimensions of the irreps of SU2, which appear in Ti, are going to correspond exactly to the linking numbers which appear associated with the D5-branes in our brane picture. So with that whirlwind tour of the classification of the boundary conditions in mind, we can move on to specifically the holographic calculation. So as we might expect, if we're interested in the holographic duals to UN n=4 super Yang-Mills theory BCFT with a certain OSP224 invariant or OSP224 symmetry, we expect that the vacuum states of these theories should be dual to some solutions of type 2b supergravity that have the same symmetry. And pretty remarkably, these were found explicitly by De Hocker, Estes, and Gupperl, who were able to manually solve the BPS equations associated with this using a certain geometric ansatz reflective of the global symmetries that we expect in the BCFT. So in particular, in our BCFT, we have some conformal symmetry, which is preserved by our boundary. And then we have some residual SO3 times SO3 R symmetry. And this is somehow reflected in the fact that the metric is some warped product of ADS4 and two spheres fibered over some Riemann surface sigma. And so they were able to determine in general what the solution to these to this half BPS, or excuse me, to the BPS equations were. And so to write down a general solution of this form in type 2b supergravity. And this solution depends just on specifying two harmonic functions of this Riemann surface. So in general, these two harmonic functions, which I've called H1 and H2, they're completely determined by their pole structure. So in particular, we just have to specify the locations and the multiplicities of the poles. And already from the fact that the geometry, the full 10-dimensional geometry needs to be non-singular, we can determine that these poles have to occur on the boundary of the Riemann surface. And so in particular, so here I've shown the Riemann surface, which canonically we can take to be the first quadrant of the complex plane. And we find that essentially the poles without loss of generality are going to lie on the positive real and positive imaginary axes. And then so our supergravity solution is completely specified when we choose the locations of these poles, which I've denoted here L and K respectively, as well as some multiplicities C and D. So basically the big takeaway from this slide is that we have some collection of these supergravity parameters, which will just be some numbers, but they will totally specify which solution we're referring to. And the idea is that by calculating certain fluxes in this full geometry, we can relate these to the linking numbers that we expect to characterize our field theory boundary conditions. So I've just, for the sake of kind of being explicit, I've written down these relations here between the field theory data and the supergravity data, but just keep in mind that we can completely specify the supergravity solution by specifying a certain collection of supergravity parameters, and these can be related in a kind of somewhat complicated nonlinear way to the field theory data. So the holographic calculation of boundary F then proceeds pretty much as one would expect. One can apply the Ryu-Takeyanagi formula to calculate the entanglement entropy of some half-ball region in our BCFT. And then one can directly extract the boundary F using that it's this universal contribution to the associated boundary entropy. And then in general, we can find an expression for boundary F in terms of some collection of supergravity parameters that I was referring to earlier. I've refrained from writing the actual explicit expression here because it's not necessarily that enlightening to just kind of stare at the full expression. But I hope the takeaway is that for a general a solution of this type, we are able to write down an explicit expression for boundary F. But we can focus in on a few interesting special cases and special features of this result. So for one, if we consider boundary conditions which involve only D5-branes or only NS5-branes, the expression for boundary F simplifies significantly, and we've written the expression for boundary F in both of these cases. A couple interesting things to note. First of all, there's a pretty simple dependence on the Hooft coupling lambda, which appears in these expressions. And then also there's a kind of manifest S-duality relating the two expressions. So we expect there should be some S-duality relationship between these two situations where we essentially exchange the D5-branes with NS5-branes. And in terms of the expressions for boundary F, what this amounts to is just exchanging our collection of D5 linking numbers with NS5 linking numbers or vice versa, and then performing some S transformation on the Hooft coupling. And indeed, this is borne out in these expressions. Another interesting feature of these particular kinds of boundary conditions is, first of all, we should keep in mind that if we're interested in a general boundary condition, which can consist of both D5s and NS5-branes, then there are infinitely many such boundary conditions which respect the symmetry that we're assuming throughout this talk. But if we restrict to a boundary condition with only D5s or only NS5s, then we essentially have finitely many boundary conditions corresponding to the finite number of partitions of the rank of the gauge group UN, since the rank of the gauge group, N, is the number of D3-branes, and the partition determines how these branes end on a collection of D5-branes. So what we find in these particular cases is that boundary F is bounded from below and above, as we would expect, since we only have finitely many such boundary conditions. But what we find is that the lower bound corresponds to the minimum entropy configuration, where we essentially have all of the D3-branes ending on a single 5-brane, whereas the upper bound corresponds to the maximum entropy configuration, where each of the D3-branes ends on its own individual 5-brane. So this is kind of nice. It's again kind of fits with our intuition about what boundary F should be measuring. Another interesting feature, moving beyond these boundary conditions where we have only D5s or only NS5-branes, is that we can see that from our expression for boundary F, that this quantity is unbounded in general. So we can kind of demonstrate this by considering a certain family of boundary conditions parameterized by some integer, which is the number of NS5-branes in our boundary condition. But we're going to consider specifically the family where we take all of the NS5-branes to have a single D3 ending on it from the right, whereas all of the D5s will have a single D3 ending on it from the left. So this family of boundary conditions corresponds to coupling in essentially some kind of complicated theory, some complicated three-dimensional theory. And as we increase the number of NS5-branes, we're essentially coupling in an superconformal field theory corresponding to some increasingly large three-dimensional quiver gauge theory. And what we find when we use this particular boundary condition in our expression for boundary F is a certain expression which has like an n squared log n behavior, where the n is the number of NS5-branes appearing in our boundary condition. And we can argue that generically we expect the corrections to our classical supergravity approximation to be comparatively subleading. So we take this to be evidence that in general, by taking boundary conditions in this family with an increasingly large number of NS5-branes, we can make this boundary F as large as we want. Moving briefly into the latter part of the talk to do with the supersymmetric localization calculation. Unfortunately, I don't have time to get into too many of the details, but essentially the general form of this calculation is that we apply a certain supersymmetric gluing formula discussed by Dedyshenko in order to write the partition function for the theory with a general NS5 type boundary condition on the hemisphere. So materially, what this amounts to is we can write the partition function for this theory as some integral, some simple integral over a set of bulk zero modes, which correspond to kind of the localization locus when we perform some supersymmetric localization of the theory on the hemisphere. And the quantities appearing in this integral are just essentially the partition function for the hemisphere theory with Dirichlet boundary conditions, where we fix the value of this bulk zero mode at the boundary. And then additionally, some partition function for a three-dimensional theory on S3, where the particular theory that we're interested in is like the IR limit of some quiver gauge theory and is determined by which boundary condition we're interested in. Fortunately, both of these partition functions have been computed previously using supersymmetric localization. So we're essentially able to import these results and then evaluate this zero-dimensional integral, a path integral, by kind of elementary means. And so the result, again, I haven't written the explicit expression here, but you can always consult the paper if you're interested. But I'll just say that we're able to write down an expression for the most general NS5 only boundary condition. We can take arbitrarily many NS5-branes and associate with them some linking numbers, and then we can write down an expression for boundary F associated with this boundary condition. And in particular, if we consider the limit where we take the linking numbers to be large and the differences between linking numbers to be large, we find that the leading order result for boundary F coincides exactly with what our calculation was from the supergravity. And this holds for any value of the Hooft coupling lambda. So this is a kind of a nice confirmation of the results, and then also a kind of nice demonstration of this holographic duality more generally. Another point that I should mention is that although we considered only NS5 type boundary conditions in order to compute this partition function and that thereby compute boundary F, in general, we can just use S-duality in order to determine what the expression should be for a D5 type boundary condition. So just to kind of briefly illustrate the kind of results that we find, what I've shown here are some histograms of exact values of boundary F. So what's happening in this picture, if we consider, for example, the picture on the left, I've fixed some value of the rank of the bulk gauge group and then fixed some value of the 't Hooft coupling, where the 't Hooft coupling is taken to be smaller than the self-dual value, which is 4 pi n. And then essentially with this n and lambda fixed, I've uniformly sampled from the collection of possible D5 type boundary conditions, and then calculated boundary F for each boundary condition that I've sampled, and then plotted some histogram of results. So on the left is the D5 case, and on the right is the NS5 case. And I've scaled both by some positive quantities just for convenience. But one immediate takeaway still from this picture is that we see that, at least in this case where we have a small 't Hooft coupling, the D5 case leads to largely negative values of the boundary free energy, or boundary F, whereas the NS5-like case leads to largely positive values. Although one thing that we should note is as I mentioned, this was for values of the 't Hooft coupling, which are smaller than the self-dual value. So when we moved the 't Hooft coupling to the self-dual value, as I recalling our earlier expressions for the boundary F and how they were related by S-duality, we see that if we actually take a lambda equals to 4 pi n, then at that point, the NS5-like and D5-like expressions will agree, assuming we choose the same set of linking numbers. And then basically the idea is that if we take the 't Hooft coupling larger than the self-dual value, then the D5-like, the boundary F for a D5-like case where the 't Hooft coupling was larger can be mapped via S-duality to an NS5-like case where the 't Hooft coupling is smaller and vice versa. So basically the takeaway here is that while I've plotted boundary F for some small value of the 't Hooft coupling, we would imagine that if I increased the 't Hooft coupling above the self-dual value, these pictures would essentially be swapped. So the D5-like case would start to look like the one on the right, and the NS5-like case would start to look like the one on the left. So just to give some brief conclusions, essentially what we've done in this talk is seen a computation of boundary F for the most general half-supersymmetric boundary conditions of the n=4 theory using holographic methods in the type 2b supergravity solutions of this type. We also computed boundary F via supersymmetric localization for the D5 type and NS5 type boundary conditions. And we found that it behaves as you would expect for a measure of the boundary, the local boundary degrees of freedom, in that it was unbounded from above. It took predominantly negative or positive values when the 't Hooft coupling is small, and we consider D5-like or NS5-like boundary conditions respectively. And it was seen to be, at least in the supergravity calculation, it was seen to be minimized or maximized on the minimum and maximum entropy boundary conditions when we restrict to D5s only or NS5s only. It's interesting to think about a few natural avenues for follow-up here. One is that it would be nice to try to use these results to perform a kind of more detailed analysis of boundary RG flows, which might occur between different boundary conditions, different half-supersymmetric boundary conditions of the n=4 theory. And it could also be interesting to use exactly the same techniques that we've used here in order to try to analyze theories that, a broader class of theories that obey the same symmetry, namely the interface theories of n=4 super Yang-Mills. But with that, I will conclude. So thank you very much, and please let me know if you have any questions.
Yeah, thank you very much for your nice talk. Are there questions? Yes, please.
I have a question.
Yeah, sure.
Please go ahead.
I was a little bit confused by all your parameters, especially about their relative size. So you had these linking numbers, which involves the number of D5 and NS5-branes, and also the difference in the number of D3-branes. But then you also have the total number of D3-branes somewhere, giving you the UN.
Yes, that's right.
So how is that compared to the other numbers?
It's
order of magnitude, I mean. Are they of the same order of magnitude, or?
Yeah, I mean, so in general, they don't have to be. Like, do you mean in order to ensure that you have like that the corrections to the supergravity approximation aren't too large, something like that?
Yes, something like that.
Yeah,
I mean, you're never in any probe limit, for instance. You're always in the full supergravity approach, or what?
Yeah, so yeah, I mean, so in general, I guess the idea is that, maybe I'll just say this: if we have some D3-branes and we restrict to either the case where we only have them ending on D5-branes or only have them ending on NS5-branes, then the number of those D5s or NS5-branes is necessarily limited. Like the maximum number that we can have is n. But depending on how many are appearing, like say how many of these five, like the number of 5-branes is scaling with n, we might expect that we would have a larger or smaller corrections to our supergravity approximation here. So in particular, for the case of like a Dirichlet boundary condition, that corresponds to just having a single D3 end on, or having one D5-brane for each D3-brane. So in that case, we sort of performed a kind of like I would say schematic analysis of what we expected the corrections to be to our supergravity approximation, essentially by zooming in on the region in the vicinity of the D5-branes in these top-down constructions, and thinking about what the contribution to boundary F was from some region in that vicinity where the curvature becomes very large, or where the string loop corrections would be expected to become large. And so we find, for example, in the case with the Dirichlet boundary conditions, where we have like a large number of D5s, that we might expect these corrections to be like comparable to the leading term appearing in boundary F. Whereas for certain other boundary, like if we take like a square root n type scaling or something, then we would generally be subleading.
Okay, yeah.
Yeah.
Okay, thank you.
Thanks.
So are there further questions? So I've got one. So you presented this localization computation, and you quoted just the result for NS5-like boundary conditions. So what is the problem if you also have other boundary conditions there? Is there a computational problem, or so?
Yeah, maybe I'll just, I can essentially say that the NS5-like boundary conditions have kind of a quite simple interpretation in terms of the field theory. So these boundary conditions essentially correspond to coupling, imposing a Neumann boundary condition for the bulk fields, but then additionally coupling in some linear quiver gauge theory, which just corresponds to essentially some collection of 3D vector multiplets. If we added some extra D5-branes in the midst, this would correspond to adding also some matter multiplets in the 3D theory. But okay, just restricting to the NS5 case, we're just coupling in some linear quiver gauge theory with vector multiplets. And so in this case, the fact that we're imposing some Neumann boundary condition on the bulk fields means that we can directly apply some previous results by the authors that I sort of flashed up there about how the hemisphere partition function can be computed in the case of Neumann or Dirichlet boundary conditions. Whereas in general, if we thought about adding in some D5-branes, this would maybe give us some more complicated non-pole boundary condition for these bulk fields. And then, I mean, I don't know if there's in principle an obstruction to trying to do some supersymmetric localization calculation, but I would say that the results are not appearing explicitly in the literature for if you have some complicated non-pole boundary condition and possibly a reduction in the gauge symmetry at the boundary, what the corresponding hemisphere partition function would look like.
Okay, good, thanks. So are there further questions? So if that's not the case, then again, thank you very much for your very nice talk. And let's conclude here the HoloTubeJunior conference series for this year. Thank you very much to all speakers.
Thank you.